In this lecture, we are going to introduce a special ADT called Heap, which is a implementation of a priority queue based on a complete binary tree. We'll talk about what this binary tree is. So Heap, let's talk about the idea of a heap, and then we'll go through the properties, the heap properties, and also some of the introductions to heap and how it is used. So the idea of a heap. So heap is a data structure. Okay. It makes use a what we call binary tree. So its underlying buffer is a binary tree that has some properties, namely it has to be complete. Again, we're talking about what this complete means. This is a data structure that keeps some of the, some comparable elements in a semi-sorted state. Okay, so remember the elements when comparable. That means it must implement comparable, or it must be able to accommodate comparators, compare. So if an element is not comparable, you will not be able to use it in a heap. So elements that are comparables are integer strings and things like that has, or even an object that has properties that are comparable, right? So comparable means that, at some point you can compare these elements vis to vis to produce either a negative one, or negative, positive, or zero, right? Outcome. So you can order these things. So heap is a semi-sorted ordering data structure, meaning the elements in there, they're not completely sorted. But what is very important about heap is you can, typically when we say heap, we're talking about max heap. So since heap is uses a binary tree, so it looks something like this, okay? The idea of, let's say, heap, which is typically what we mean by max heap, is that you have the highest ordered or highest priority item sitting at the root level. And that is very important, because if you have the most important elements that you're looking for at any given time, right, namely the maximum, right, the highest priority item at the root, then what does that tell you about this fetch, meaning search time, or get, or insert? It's O of 1, right? Because once you recall that tree starts with roots, right? If the root is what you're looking for, then O of 1, right? So in fact, in a binary search tree, the largest elements, or the highest priority elements, is always at the roots of the tree, right? And larger elements would tend to be at the near the top of the tree. So you have something like this. The order of importance kind of goes up, right? From the bottom, the children, from the leaves, all the way to the roots. This is what we call max heap, okay? Max heap. So in fact, the inverse is true. You can build what's called a minimum heap. So minimum heap is the opposite of your max heap. In this case, the minimum or the lowest priority item will be at the top, and the minimal value will be at the top, right? And then the obviously in that case, the order of importance kind of goes down, right? From ordering actually goes up, right? For a minimum heap. It starts from the root being the lowest priority, and then all the way down to the bottom, where you get the highest priority on the bottom, or the higher priority items. Now, so we alluded to this thing being semi-sorted, okay, semi-sorted. So in fact, the order of these elements are not, once you get past, right, the root level, whatever is on the bottom, they generally keep there's a sense of ordering, but the sense of ordering is very generically termed as greater than or equal to the value in each of the children. It's not as stringent as what you would see, for example, in the binary search tree, where left and right distinctions in terms of the order values. But in heap, we don't really take care of the exact or specific ordering of these inner nodes dependency with their children's. We care about only the top one, right? Only the top one, either either a being max or a minimum priority item. Okay, so that is kind of the idea of a heap, as you can imagine, right? So the idea that we want to have this heap is to make sure that, just like priority queue, right, where the important operation are to insert a new element, right, and remove the largest elements. And that's it, right? We don't really care about the intermediate. We don't care about if this node is maybe the fourth highest priority item or the fifth high. We don't really care about that. We care about the most or the highest value nodes that we want. We want to optimize its insertion time, and removal time, right? Insertion, removal. If this all happens at the node, at the roots level, that's what this heap is really about. Okay. So I wanted to preface this. And the other thing about this tree, like I said, is a binary search tree. So let's just talk about the two major properties for a heap. So formally, a heap, right, is a complete tree of comparable elements that satisfy the heap properties. The shape property. The tree must be a complete binary tree. So we'll talk about complete versus full or other types of binary trees in the next node. But binary tree means each node having two children. Okay, that's what a binary tree is. So that's our premise here to begin talking about the shape property. The other property of heap is the order property. So for every node in the tree, the value stored in the node is greater than or equal to the value it needs of the children. So this is true for what we call max heap. Okay, so this is max heap. And if this is greater, right? But if this is lower than, right, or equal to the value in the children, but just by changing this thing, then we're talking about minimum heap. Okay, so there's a semi-ordered property, and there's a shape property. So let's talk about both of these in the next slide. So what is a full binary tree? Well, a full binary tree, sometimes we call them a binary tree or two dash tree, right? It is a tree in which every node other than the leaves having two children, has two children. So this means this one is a binary tree, okay? Or you can have multi-level full binary tree. Basically, it's a symmetrical tree. There's not a missing node, okay? So basically, this is all completely filled. So this one is very easy to remember, right? So as long as you see a tree, and this tree is a binary tree, and it has a middle plane that is, allows you to kind of fold this right into it, and they're symmetrical. This is a full binary tree, right? So full binary tree generally has this triangle shape, right? Like your Christmas tree, right? Anyway, so that's a full binary tree. Complete binary tree. Now, this complete binary tree is very interesting. It's, it's not really a complete, I mean, if you look at this, I mean, a tree cannot be complete if it's missing a chip, right? But that is indeed how it's defined. I don't know why they call it complete tree. To me, this is an incomplete full tree, okay? Incomplete, but full. Almost full, but it's incomplete tree. So, well, in computer science, we call them, CBT. This is a complete binary tree. So when you see a tree that kind of falls into this, so first of all, a complete tree is a binary tree in which every level, right, except possibly the last, right, is completely filled. And all of the nodes on the very last levels are as far left as possible. So this is your last level. And this level is just missing this part to the right. So you can have something like this, basically one node and having this node, but it's missing this part. This entire part is all missing. This is missing. This is what we call complete binary tree, okay? And it's just missing the right. So basically, you look at the very last level, it's missing the right side, okay? So you can also have this one, but and the rest of the nodes are flushed to the left as much as possible. You can also have something like this. This is 3 levels, right? In this 3 level, what you have is you have something like this, and it's just missing this very last one, right? It's missing this very last one. This is what we call a complete binary tree, okay? Look at the last level, it's just missing the nodes on the right side. You can also be missing 2 of these. It's just missing stuff, and or even this, okay? At this point, it's just missing everything on the right side. But everything else is kind of flushed all the way to the left. So that is what we call a complete binary tree. And interestingly, a full tree is also a complete binary tree. So another definition of complete binary tree is let's say if you only have one level and that level is completely filled, or several levels that are both really completely filled, that's considered a complete tree also, okay? So complete tree kind of encompasses both. Actually, no, a full tree encompasses both the full tree and the definition of a complete binary tree, right? But not the other way around. The complete binary tree, since it's missing this chip right here, missing some spec. It's not a full tree, right? But a full tree is a complete tree. So I just wanted to make that absolutely clear. And what do we say about heap? Well, a heap says the tree property, right? The heap says that the tree must be a complete binary tree. So this means that if we have a full tree, which is by definition a complete binary tree, then that full tree could be used as an underlying data structure for heap. So in other words, another way of saying is heap can either be using a tree that is either complete or full. Okay, so this is not here, but I just wanted to make that really, really, really clear. So that is the definition of a tree in terms of fullness and its completeness. Let's talk about let's just use some examples here. So as you can see here, this one is complete in full. Okay, so again, the a complete tree has its leaves right on one level, right? One level, which this is one level, and there's actually two coming off of it, and they just turn out to be null, right? Null. Okay, so that's considered a complete tree. Or on the two adjacent levels. So in this case, this level and this level, right? Two adjacent level, right? The two adjacent level use case, the leaves on the upper level all exist, and those on the lower levels are left justified. So this is missing, right? But on the very last level, all of the nodes are left justified, right? Shifted to the left. So this is qualified as a complete tree, right? So is this one, right? Because this one is missing this part, and the last level is this level, and the node here, this child, is left justified. So what you have is basically a tree that looks like this, right? So it's got this shape right here, and this chip, this broken piece is always on the bottom lower right side. This one is not though. This is not a complete tree because it's missing this part, right? This entire thing. So you have to make sure that all of the upper levels are all filled, okay? The only part that is not filled is on the bottom, okay? So you can have a piece that only has the left child, but is missing the right child. So it's okay to have something like this too. So this would consider a complete tree as well. But since it's missing the both levels, this is not a complete tree. And obviously, right, none of this is a full tree, right? Full tree has to be symmetrical, like one itself, or having a profile that looks like a Christmas tree. Okay, so so that's that. This is the shape property, right? So if we go back in there and look at this other property, which is called a order property. For every node in the tree, the value stored in that node is greater than or equal to the value in each of its children. So this is what we call max heap. So this means that the element must also be larger than elements in any of its descendants. So let's move on to this illustrations here. So we're using a English alphabet here, right? So A is obviously the lowest, right? If we use the alphabetics and saying that the A's got the lower priority, right? Then B. So this will be, if you're using string, this will be its natural order. Naturally, B is greater than A, and assuming this is all capital, right? And then dot, 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 and Z being the biggest one. And as you can see, this is exactly what we have here. So J is the largest element, right? In this case, largest element. But what you have is you can have, the ordering, the descendant ordering being in this fashion, A, or this fashion, right? Now, what does that tell you? This tells you that what you have here is a maximum heap. Both are valid because there are, first of all, a complete binary tree, right? It's missing this chip right here. But the ordering is a little different, right? This underlying, right, the ordering of the descendants. This is precisely what I meant by semi-sorted, okay? So a heap is semi-sorted. The only thing that is sorted is really just the most important one at the root, because we want to maximize our insertion and find, right? So we give we're basically, at any cost, at the expense of, just keeping this O1, just getting it. We don't really care too much about the specific value. We care about one thing, and that is all of the descendants on top, right? The top descendants will have value higher than the greatest. So if you look at any, like even this inner node right here, H is greater than D, is greater than G, is greater than E, and G is greater than E right here, right? I is greater than both F and A, right? But with respect to either A should be here, right, or A should be here, it doesn't really matter, right? So Heap doesn't really care about the descendant order, but they generally have to follow the binary, tree structure, having, these leveled order property, generally speaking. But the strictest order is the biggest one has to be on top, right? So that is maximum heap. Minimum heap is the opposite, right? The minimum one is going to be on top. So that's what we are interested in. And hopefully this lecture gives you, this intro gives you a good understanding of the heap property, the idea, right, for using a heap, and also some of the introductions that you see here. So just remember the shape property. The tree must be a complete binary tree. It could also be a full tree, right? The order property, right? So for the highest node, at the highest priority node, it's going to be on top. And then every forthcoming levels down below is going to have values greater than its descendants, so on and so forth, until we reach the end. So that would be a good sort of the two things that you wanted to understand and perhaps memorize before using this heap. And then we'll talk about the InQ and DQ, how these things work in terms of heaping up and down in the specific implementation details.